Hello. So today we're going to continue our discussion that I started last time on inaccessible cardinals. So this is section 2.6.1, page 35. Now, an inaccessible cardinal I can think of as being something that is, well, it's inaccessible. You can't reach it either by the successor operation, going from one cardinal to the next, and so aleph omega is like that. You go from aleph 1, aleph 2, aleph 3, aleph n plus 1, and you can't reach aleph omega in some successor step like that. But aleph omega is singular. It's the cofinal result of going through the aleph n's. But a regular limit cardinal is one where you can't access it by this successor step operation, nor do you have some function from below with some smaller domain, unbounded cofinal into that cardinal. So it's a fixed point of the enumeration of the alephs. So in that sense, it's a large cardinal. And actually, it turns out we can't prove that these cardinals exist in our set theory. If we want them to exist, we have to make an extra assumption. And as I've said before, set theorists are fond of enlarging the axioms of ZFC with so-called large cardinal hypotheses and teasing out what the consequences are. But we're just going to look at the very basic definitions here. I'd like to point out that the discussion continues in section 2.6.2, but we're omitting that. That's not part of the course. So we're only going to discuss page 35 and the top of page 36 before we move on to the next chapter. Okay, so let's continue. See here that we discussed this to some extent yesterday. So I'm just trying to change my view. Something has slightly happened here. So I'm still stuck here. Okay, fine. Except now my chat has disappeared. Okay, I seem to be back again. Sorry about that. Don't know quite what that meant. Yesterday, I won't go through this page again. I talked about just some preamble about inaccessible cardinals there. I'll just move straight to the definition, which is top of page 35. So definition 246. So a cardinal is, an uncountable cardinal is a strong limit cardinal. So definition 246. Cardinal kappa bigger than omega is said to be a strong limit cardinal if whenever alpha is less than kappa, then 2 to the alpha is less than kappa. More strictly speaking, we should say this is true if alpha is a cardinal, but maybe alpha is an ordinal. So I'm saying 2 to the cardinality of alpha is less than kappa. So if alpha is a cardinal, okay, we just write 2 to the alpha is less than kappa. So the idea here is I can't access kappa, I can't make it accessible by finding a smaller cardinal whose, well, power set is larger. This is the cardinality of the power set of alpha here. In particular, if alpha is an ordinal, again, I should write this. This, after all, is defined to be the cardinality of the set of functions from this into 2. And I identify that with characteristic functions of subsets of alpha. So a strong limit cardinal is one who I pick any cardinal alpha less than kappa, its power set has got size less than kappa. So it's not only that, so I can't access kappa by using the power set operation. So 247. So a regular cardinal so the nomenclature is, it's said to be weakly inaccessible if it is a limit cardinal. Right, so it's a limit in the enumeration of the alephs here. But its cofinality is itself. It's said to be strongly inaccessible if in addition it's a strong limit cardinal. Means you're going to be regular, but you're not going to be able to access kappa using the successor function, and nor can you find a smaller cardinal alpha whose power set is larger. So it's like I can't access it using the power set operation either. So you can see this is a stronger closure property on kappa than this one. Here we only say we can't access it using the successor cardinal operation. Here we can't access it either using the power set operation. So we often, if I use the word inaccessible by itself, that's because we often drop the strongly here. Right? So there are some notes below. So the word strongly is often omitted. we're usually considering strongly inaccessible cardinals. So kappa is weakly inaccessible. So there's two, just restating it another way. It's got to be regular. And B, if alpha is less than kappa, then alpha plus is less than kappa. And again, to contrast with strongly inaccessible, if it's regular, and B, if alpha is less than kappa, then 2 to the alpha is less than kappa. Notice that this subsumes this because by Cantor's theorem, this is greater than or equal to the next cardinal beyond that of alpha anyway. So this is potentially a stronger condition. Of course, the generalized continuum hypothesis might hold, and this might just be alpha plus, in which case we wouldn't have any difference between strongly and weakly inaccessibles. So if the GCH holds, there's no difference between strongly and weakly inaccessibles. As then, if alpha is in a cardinal, 2 to the alpha equals alpha plus anyway. So the condition that alpha plus is less than kappa is the same as the condition that 2 to the alpha is less than kappa. But that's if, right? Notice that at the top, there was no conditioning on kappa being regular. And one can check the first strong limit cardinal actually has got cofinality omega. So we can prove strong limit cardinals, singular strong limit cardinals exist. The least strong limit cardinal has cofinality omega. Okay, so this is a little exercise. Check. That's the case. If the GCH holds, aleph omega is the least strong limit cardinal. Then I have that 2 to the aleph n is aleph n plus 1. And so if alpha is if alpha is less than aleph omega and alpha a cardinal, 2 to the alpha is less than aleph omega. So aleph omega is then the least strong limit cardinal. So in this case, Aleph omega is the least strong limit cardinal. So that was under the supposition that GCH holds. But it may be that 2 to the Aleph 0 is bigger than Aleph omega, and this may, so that means Aleph omega can't be the first strong limit cardinal. So it's consistent with the axioms by the work of Paul Cohen that 2 to the Aleph 0 is bigger than Aleph omega. So in this case, we couldn't have that Aleph omega is a strong limit. So it's consistent that it is not a strong limit. In our proof of, in our construction of L, which is the main point of this course, we'll see that the GCH holds in L. So that will mean that it's consistent that Aleph omega is a strong limit. So it could go either way. Okay, so let's look at lemma 248. And again, I'll emphasize that we're using AC in here. So pick an uncountable regular cardinal, kappa. Then the following are equivalent. And kappa is strongly inaccessible. That V kappa is the same as H kappa. That all the axioms of ZFC hold in H kappa. And that kappa equals Beth kappa. So I'll just remind us then what Beth kappa, the Beth hierarchy is. Beth 0 is Aleph 0. Beth alpha plus 1 is 2 to the Beth alpha. So instead of going to the next cardinal, we're going to the next power set each time. And if lambda is a limit, Beth lambda is the supremum of all the previous ones. So whereas the Alephs enumerate all the cardinals, the Beths just pick out the results of cardinal exponentiation. And again, if GCH holds, Beth alpha is the same as Aleph alpha. So being a strong inaccessible means you are a regular fixed point of the Beth function. This Beth function here, it's picking out a closed unbounded class of cardinals. The range of this Beth function, these cardinals that it's picking out, right, forms a closed unbounded class. So the Beth function is a normal function. See, we've got continuity here at limit stages. That's one observation. 3, of course, is an important one, right? We've got all of the axioms of ZFC holding in H kappa if kappa is strongly inaccessible. So that just tells us straight off, we can't prove in ZFC there exists such a kappa. Because if there were, we'd prove in ZFC the consistency of ZFC, because we'd find a structure in which those axioms were true. So they have to be consistent. So main remark then here is ZFC does not prove there exists kappa bigger than omega, where kappa is regular. Well, I just say strongly inaccessible. Because ZFC can't prove there's a model of, in other words, since ZFC cannot prove there's a kappa bigger than omega, where the axioms of ZFC hold in H kappa. I'll put it slightly informally like that. So if you are a firm believer in ZFC and nothing else, you may think this is all fiction. There's no reason to believe there are strongly inaccessible cardinals if you're a ZFC fanatic. Okay, so we're going to look at the chain of implications here. So we'll just go in a cycle around the various clauses here. And we'll just look at the definitions. Sorry, we'll look at the consequences that we have. Kappa is a regular cardinal, right, here. So kappa cardinal, this already implies that H kappa is contained in V kappa. So we have one inclusion here already. This was lemma 231. So it's the reverse inclusion we need to establish to get 1 implies 2. Okay, so pick an x in V kappa. I want x to be in H kappa. But if it's in V kappa, kappa is a limit ordinal. So V kappa is the union of the smaller V alphas. So we'll just show by induction that for alpha less than kappa, that all of these V alphas have got size less than kappa. That will do because H kappa is the collection of transitive sets of size less than kappa. And V alpha will then be a transitive set of size less than kappa. So by induction on alpha, we show that cardinality of V alpha is less than kappa. Since V alpha is transitive, this means V alpha then is a member of H kappa. And since X is in V alpha, X will be in H kappa. Because the H's are also transitive. So it suffices to show this. And as I said, by induction on alpha less than kappa. So let's suppose as an inductive hypothesis it's true for beta less than kappa. Sorry, for beta less than alpha, and we'll prove it for alpha. So there are two cases. Alpha is a successor or alpha is a limit. So if alpha equals beta plus 1, by the inductive hypothesis, V beta's got size less than kappa. And then, of course, V alpha is just the power set of V beta. I mean, this just is here V alpha. So the power set of V beta, right, has got size 2 to the size of V beta. But by the inductive hypothesis, right, the size of V beta is less than kappa. As kappa is strongly inaccessible, this is where we use the strongly inaccessible assumption. This is less than kappa. So kappa is assumed strongly inaccessible. Okay. So yes, we're using the inductive hypothesis as well. We're assuming that we know the cardinality of VP is less than kappa, and then as kappa is strongly inaccessible, 2 to that cardinal is less than kappa. So that does 1 implies 2. Okay, so don't know if there are any questions there. And we'll just continue. Let's do 2 arrows 3. So V kappa equals H kappa. We want this to give us to yield that ZFC holds in H kappa. Well, actually, we know we've done most of the work of this already. We already know that for kappa regular, that all of the axioms of ZFC minus hold in H kappa. This was an earlier lemma. What is it? 232. So all that's missing is the power set axiom. So we just make an observation. We note that any V lambda, the lambda limit, is a model of the power set axiom. Because what is V lambda? It's the union of the smaller V alphas, each one of which is the power set of its predecessor. So if X is in V lambda, there is an alpha less than lambda, such that x is in V alpha. And then power set of x is, let's see, power set of V alpha equals V alpha plus 1. Okay, that is also a member of V lambda, because lambda is a limit here. And so I want to say that power set of x is in V alpha, so its power set is contained in the power set of alpha so it's, I mean, so for any x in V lambda, its power set is in there. And fortunately, 2 says when lambda equals kappa that this equals h kappa. So now our assumption 2 is that h kappa equals V kappa. Sorry, and this is a limit. So the axiom of power holds in h kappa as well. So in fact, together with the earlier result, I've got all of ZFC holding in h kappa. Three arrows 4. So we want to show kappa is Beth kappa, right? Recall this is the supremum, or the union, if you like, of the Beth alphas for alpha less than kappa here. This is what we want to show. So it suffices to show, right, that if alpha is less than kappa, then Beth alpha is less than kappa. So if alpha is less than kappa, each of these is less than kappa. Because then the supremum we're taking here of all of these things over kappa many objects has to be kappa itself. So we will get this equation here. This is by definition. So I just want to show that kappa is closed under the Beth operation. And we're allowed to assume that H kappa is a model of ZFC. So we use the axiom of ZFC to show that for every alpha, there is a Beth alpha, basically. Okay, so by induction then, as always. Assume this is true for beta less than alpha. So again, if alpha is a successor, then what is Beth alpha? It's 2 to the Beth beta But now I deploy the axioms that I know hold in H kappa. I know I have AC, and I know I have the axiom of power. This all holds in H kappa. So this here, I'm thinking of this as the cardinality of the power set of Beth beta. So by the axiom of choice, I've got a bijection between this power set and an ordinal. So by AC, I know there is an ordinal, so that Tor is bijective with the power set of Beth beta. That's what we do. We assume AC, or the well ordering principle, that says that every set can be well ordered in the order type some ordinal. So there's always a bijection between an ordinal and any set. And that's all I'm using there of AC. So if I've got that this set is bijective with this ordinal, then the cardinality of this set is less than or equal to this ordinal. So what I have then, this is 2 to the Beth beta, which I said is this here. So I mean, H kappa, it thinks already by inductive hypothesis, Beth beta is a set. It's one of its ordinals, and it's got size less than kappa. So H kappa sees Beth beta. It's a model of the axiom of power set. So it thinks there is a power set of this Beth beta. It's a model of the axiom of choice. So there's a bijection between this set and this. Right? So this, sorry, I should really perhaps put this here. Yeah. So this sentence is true in H kappa about Beth beta. So H kappa sees that there is an ordinal bijective with this set that it's got hold of. So of course, this ordinal, the ordinals in H kappa are precisely kappa. So this is an ordinal less than kappa here, which is what we wanted, that 2 to the Beth beta, which is Beth alpha, is less than kappa. This is what we're trying to show here. So that finishes the successor case. If alpha is a limit here, then what are we saying? Beth alpha is the supremum of all the smaller Beth betas. So this Beth alpha has got cofinality alpha. Okay, so as alpha is less than kappa, and because kappa is regular, its cofinality is kappa here. Here we use the assumption that kappa was a regular cardinal. So this increasing sequence is too short to reach up to kappa. So Beth alpha is less than kappa. So in either case, alpha a successor here or alpha a limit, Beth alpha is less than kappa. So it finishes there. So finally, we complete the circuit by proving that 4 arrows 5. Here. Sorry, 5, 4 arrows 1. Well, we appeal to an earlier exercise, 2.9. Shows that the size of V omega plus alpha is Beth alpha. After all, when we go up the V hierarchy, we just go power set, power set, power set at each stage. And that's just what these cardinalities are doing. They're saying each one is the cardinality of the previous level of the V hierarchy, if there is a previous level. And the omega that's in here, this is just a wrinkle because we start off with Beth 0 being omega, right? So the numbering goes a little funny. If alpha is at least omega squared, then actually omega plus alpha equals alpha. So I can forget this omega plus bit, right? Recall omega plus omega squared, right? If you're wondering why this is, by ordinal arithmetic, it's just this. By a distributive law, 1 plus omega is just omega. So this is just omega squared. And similarly for ordinals, alpha bigger than omega squared. So our assumption 4 is that kappa equals Beth kappa. So I can write this. And you can forget about the omega squared bit at the beginning. Right? 2 to the size of alpha is the power set of size of the power set of alpha. But the power set of alpha, this is less than or equal to the size of the power set of V alpha plus 1. Recall alpha is a subset of V alpha. So the power set of alpha is no larger than the power set of V alpha. And this is the power set of V alpha here. And now we use this here. This then has got size. Here, Beth alpha plus 1. And so this is less than kappa. I took an alpha less than kappa, so alpha plus 1 is less than kappa, so Beth alpha plus 1 is less than kappa. So that makes kappa strongly inaccessible. And that completes the circuit. Okay, don't know if there are any questions there. Okay, I'll just draw your attention to the exercises that are there. 246 just says rephrase the definition of being strongly inaccessible. Sorry, weakly inaccessible. If kappa is irregular, and kappa is actually a fixed point of the Aleph function. What we just showed was if kappa is strongly inaccessible, if and only if kappa was regular and it was a fixed point of the Beth function. This is the weaker version of that. Kappa is strongly inaccessible if kappa is regular and kappa equals Beth kappa. That's the difference between that exercise and what we just did. And you can test your understanding of all this by answering the following question. If kappa is bigger than omega and H kappa equals V kappa, does this imply that kappa is strongly inaccessible? So again, if you've understood what's going on here, this is kind of a one-line answer once you've found the right reason. Right? Or 2 lines, perhaps. I don't know. Okay, fine. So the next recorded lecture, we'll talk a little bit about Marlowe cardinals. It'll just finish the few paragraphs left in 261, and then we'll move on to chapter 3. We'll start looking at how to arithmetize our syntax, and I'll give some reasons as to why we'll be interested in doing that then next time. Okay, I'll see you then.